You hit a pocket of rough air, the plane bumps, and then the flight smooths out. This is the turbulence most passengers expect. But at 30,000 feet, aircraft can sometimes fall into a different pattern, a bizarre, repeating figure-8 swaying motion. This motion is called a Dutch roll. It's a complex, coupled aerodynamic event where movements become out of phase. In this diagram, the nose wags left and right, yaw, while the wings simultaneously rock up and down, roll. The curved lines trace the resulting corkscrew trajectory. Inside the cabin, the sensation mimics a rocking chair tipping side to side, while the back of the seat wags left and right. The physics are similar to an ice skater gliding across a frozen pond. To move forward, a skater shifts their weight from one leg to the other in a rhythmic sway, trading momentum back and forth. While most Dutch rolls are stable and will eventually settle on their own, the motion is hazardous if left unchecked. If the oscillation is allowed to grow, it can escalate into a total loss of aircraft control. This motion is a byproduct of the aircraft's own design. The Dutch roll occurs when a plane's high-speed aerodynamic features begin to compete with its own stability. This scale illustrates the primary conflict in aircraft geometry. It is a constant tug-of-war between directional stability, the desire to keep the nose pointed straight, and roll stability, which keeps the wings level with the horizon. To achieve the speeds required for modern travel, airliners use swept wings that angle backward. While efficient, this design creates a massive amount of roll stability, pulling the tug-of-war heavily to one side. A sideways slip makes the forward-angled wing catch more air, creating lift that rolls the aircraft up. This extra lift causes drag, pulling the wing back and twisting the nose. The opposite wing then catches the wind, repeating this self-feeding, rolling, and yawing loop. These oscillations are most common at high altitudes, where the air is thin. With fewer air molecules to provide natural damping, or aerodynamic friction, there is very little to cushion the sway. A Dutch roll indicates an aircraft is highly effective at leveling its wings, but lacks the directional strength to keep its nose pointed forward. Engineers could theoretically solve this by making the tail more powerful, ensuring the nose-straight side of the tug-of-war always wins. However, prioritizing directional stability over roll stability creates a different hazard: spiral instability. This diagram tracks a spiral's path. A minor disturbance causes a slight bank. Because the nose stays straight, the plane turns. The outer wing moves faster, generating more lift. With weak roll stability, the bank increases, dragging the aircraft into a tightening, descending turn. This unrecoverable descent is known among pilots as the graveyard spiral. Engineering safe aircraft requires precise balance. Too much roll stability leads to a dizzying sway. Too much directional stability leads to a fatal spiral. Because swept-wing jets are susceptible to these sways by design, engineers developed a way to neutralize the motion before it starts. Modern aircraft use a yaw damper. This tail section schematic shows an automated shock absorber linked to the rudder. It detects the first micromillimeter of a sway and adjusts the rudder in the opposite direction, instantly canceling the oscillation and keeping the flight path straight. If the automated system fails, the responsibility shifts to the pilots, who are trained specifically to recover from a manual Dutch roll. The first step in recovery is resisting the urge to react violently. Abrupt steering corrections can inadvertently add energy to the loop, making the swaying more severe. Pilots instead use smooth, coordinated inputs. They adjust the ailerons, the flaps on the wing that control roll, and the rudder in sync. This timing interrupts the feedback loop and brings the nose back to center. The stability of your flight relies on this managed aerodynamic balance. A smooth journey is the result of sophisticated automated sensors and the precise training of the crew in the cockpit.